Welcome to this walkthrough of LeetCode problem number 1747, cannot retrieve specific problem details.
In this session, we'll systematically explore the approaches to solve this problem, discuss potential complexities, and highlight key insights you can use in similar challenges.
Let's dive in.
The problem description for LeetCode problem 1747, titled Cannot Retrieve Specific Problem Details, is not currently available.
This could be due to the problem being locked or restricted. To access these details, please visit the LeetCode website and navigate to the problem directly. We recommend ensuring that you are logged into your LeetCode account, as some problems may require a subscription to access additional content such as test cases and constraints.
Unfortunately, no further details can be provided at this time.
When tackling algorithm challenges, a systematic approach is key, especially when specific problem details are unavailable. We start by considering multiple broad strategies that apply to common problem types like graphs, dynamic programming, strings, and arrays. One fundamental method is the brute force approach. This involves exhaustively examining all possible solutions to the problem. For example, in arrays or strings, you might iterate over all pairs, substrings, or subarrays to evaluate every combination. In graph-related problems, you could use exhaustive searches such as depth-first or breadth-first search to explore all possible paths. Similarly, in dynamic programming, a brute force approach might involve writing a recursive solution without optimizing for redundant computations. While this method guarantees correctness, its major drawback lies in its inefficiency. Time complexity often grows exponentially, making it unsuitable for larger inputs. Despite this, brute force is invaluable for identifying patterns or insights that can lead to more refined solutions. Optimizing beyond brute force requires leveraging the specific properties of the problem. Divide and conquer is one such approach, where the problem is split into smaller, independent subproblems that can be solved individually before combining their results. This is a common theme in algorithms like merge sort or binary search, which achieve significant efficiency gains. Another powerful strategy is the greedy approach, which focuses on making locally optimal decisions at each step to achieve a globally optimal solution. This is especially effective for problems involving intervals, weights, or priorities, such as interval scheduling or Dijkstra's algorithm. Beyond these, dynamic programming with memoization is essential for problems with overlapping subproblems and optimal substructure. By storing intermediate results, we eliminate redundant work and improve efficiency. Classic examples include the knapsack problem and computing Fibonacci numbers. For even more sophisticated cases, advanced data structures like segment trees, Fenwick trees, or tries come into play. These structures allow for highly efficient operations such as range queries, prefix computations, or string matching, often reducing time complexity to logarithmic scales for specific tasks. To solve any problem effectively, the chosen strategy depends heavily on the problem's category and constraints. The process begins with a clear understanding of the input types, whether they involve arrays, strings, or graphs, and their constraints. From there, analyzing smaller test cases or edge cases can reveal patterns that guide the solution. The next step is selecting an appropriate algorithm. Depending on the problem, this might involve brute force for simplicity, divide and conquer for breaking down complexity, dynamic programming for problems with overlapping subproblems, or advanced data structures for optimized operations. Optimization is then crucial to ensure scalability, balancing runtime complexity and memory usage. Each method comes with trade-offs. Brute force is straightforward but computationally costly, making it better suited for validation rather than efficiency. Greedy algorithms are faster but rely on problem-specific conditions to guarantee correctness, while dynamic programming is more flexible but requires additional space. Advanced data structures provide unmatched performance for certain tasks but are harder to implement and debug. The ultimate choice of strategy balances correctness, efficiency, and ease of implementation, ensuring the solution meets the problem's demands. To tackle an algorithm challenge systematically, we first need to understand the problem thoroughly. Start by carefully analyzing the example inputs and outputs to identify the problem's key components. Is this a shortest path problem, a question about connectivity, or something else entirely? Pay close attention to the constraints provided, such as the size of the graph, whether the edges are weighted, and if the graph is directed or undirected. These details will help narrow down the optimal approach. Once you've understood the problem, the next step is to represent the graph. An adjacency list is often the best choice because it is memory efficient and easy to traverse. For a graph with n nodes and m edges, you can use a dictionary where each node maps to a list of its neighbors. For example, you might represent the graph as adj equals node list of neighbors. This representation is simple yet powerful for most graph-related problems. The next step is to choose the right algorithm based on the problem requirements. If you need to find the shortest path, use Dijkstra's algorithm for weighted graphs or BFS for unweighted graphs. If cycle detection is the goal, a depth-first search with a visited set and recursion stack will work well. For finding connected components, both BFS and DFS are effective options. Let's assume our focus is on finding the shortest path in an unweighted graph. To implement BFS for this, begin by initializing a queue to store pairs of the form node distance. Start with the source node and set the initial distance to 0. For example, q equals dec source 0. Alongside the queue, maintain a visited set to track nodes that have already been processed, which prevents revisiting and avoids infinite loops. For instance, you can initialize it as visited equals set. During traversal, while the queue is not empty, dequeue the front element to get the current node and its distance. If the current node matches the target, return the distance. For each neighbor of the current node, check if it's unvisited, mark it as visited, and enqueue it with an increment distance. It is equally important to handle edge cases in your BFS implementation. For instance, if the target node is unreachable, the function should return -1 or an equivalent value indicating failure. Once the implementation is complete, analyze its complexity. The time complexity of BFS is O, V plus E, where V is the number of nodes and E is the number of edges. This is because BFS processes each node and edge exactly once. Space complexity is O, V, due to the storage required for the queue and the visited set. BFS is particularly suitable for unweighted graphs because it explores all nodes at the current distance level before expanding further, ensuring the shortest path is found. The visited set is a crucial component of the algorithm, as it ensures each node is processed only once, eliminating redundant work. Additionally, edge cases such as disconnected graphs and single-node graphs should be handled gracefully. For example, if the graph has only one node where the source is the same as the target, the algorithm should return a distance of 0. To bring everything together, let's discuss the data structures used. The adjacency list efficiently represents the graph structure, while the queue facilitates level-order traversal in BFS. The visited set ensures nodes are not revisited, maintaining linear time complexity. Consider this example graph, adj equals 1, 2, 3, 2, 4, 3, 4. The source node is 1, and the target node is 4. Initially, the queue is set to dec 1, 0, and the visited set is empty. In the first step, dequeue 1, 0, and queue its neighbors 2, 1, and 3, 1, and mark node 1 is visited. Next, dequeue 2, 1, and queue its neighbor 4, 2, and mark node 2 as visited. Then, dequeue 3, 1, find no new neighbors, and mark node 3 as visited. Finally, dequeue 4, 2, which matches the target. The algorithm returns the shortest path distance of 2, demonstrating the efficiency of BFS in finding the solution. For more advanced scenarios, optimizations can further improve performance. For weighted graphs, using a priority queue or heap enables efficient implementation of Dijkstra's algorithm. When working with very large graphs, bidirectional BFS is a powerful optimization that reduces the search space by simultaneously exploring from the source and target nodes. Finally, this systematic approach ensures clarity and flexibility, allowing you to solve a wide variety of graph-related problems effectively. By combining the right data structures, appropriate algorithms, and careful consideration of edge cases and optimizations, you will be well equipped to tackle challenges in competitive programming and beyond. Here, we're implementing a solution to a generalized graph traversal problem, which often comes up in algorithmic challenges. We start by defining a class called solution and a method shortest path that takes in the number of nodes n, a list of edges, and 2 nodes start and end. First, we construct the graph as an adjacency list, initializing a dictionary where each node maps to an empty list.
Then, for every edge in the input, we add the connected nodes to each other's adjacency list to represent the undirected graph. Next, we initialize a breadth-first search, or BFS, to find the shortest path. The BFS queue is initialized with the starting node and a distance of 0, and we also maintain a set to track visited nodes to avoid revisiting them. We begin the BFS loop by dequeuing the front element, which gives us the current node and the distance traveled so far. If the current node matches the target node, we return the distance as the shortest path length. Now, within the BFS loop, we explore all neighbors of the current node by iterating through its adjacency list. For each unvisited neighbor, we mark it as visited and enqueue it along with an increment distance, representing the path length from the starting node. This process ensures that we systematically explore paths of increasing lengths, guaranteeing that the first time we reach the target node, it is via the shortest path. If the queue becomes empty and we haven't reached the target node, it means no path exists, so we return -1 as the result. At the end, we demonstrate the usage of this method with an example graph containing 6 nodes and several edges. Starting from node 0 and targeting node 5, the method calculates the shortest path length, which in this case is 3. This example showcases how BFS efficiently finds the shortest path in an unweighted graph. Here, we begin by defining our Java solution to find the shortest path in an undirected graph. First, we create an adjacency list representation of the graph using a hash map, where each node is mapped to a list of its neighbors. This allows us to efficiently store and retrieve the connections between nodes. We then iterate through the edges array to populate the adjacency list, ensuring that each edge is bidirectional since the graph is undirected. After setting up the graph, we use a breadth-first search, or BFS, approach to explore the shortest path. To initiate the BFS, we declare a queue that will keep track of nodes along with their respective distances from the starting node. We also maintain a hash set to keep track of visited nodes, ensuring we don't revisit them, which helps avoid infinite loops. The BFS begins by enqueuing the start node with a distance of 0 and marking it as visited. While the queue isn't empty, we process each node to explore its neighbors and calculate distances accordingly. If we encounter the target node, end, we immediately return the distance, as it represents the shortest path length at that moment. Now, if the target node is not yet reached, we proceed to explore the current node's neighbors. For each neighbor, we check if it has already been visited. If not, we mark it as visited and add it to the queue with an increment distance, representing the path length from the start node through the current node. This ensures that we explore all possible paths in increasing order of their lengths, a hallmark of the BFS algorithm. If the queue eventually becomes empty without reaching the target node, it means no path exists between the start and end nodes, so we return -1 as the result. Finally, we demonstrate the usage of this method in the main function with an example. Here, we define a graph with 6 nodes and edges connecting them to form a simple structure. The start node is set to 0, and the end node is set to 5. The shortest path method is called with these inputs, and the result is printed to the console. In this example, the output is 3, which represents the shortest path length from node 0 to node 5. With this, the program concludes after successfully printing the shortest path length to the console. The combination of BFS for pathfinding and the adjacency list for graph representation ensures that the solution is both time-efficient and easy to understand. This approach is particularly useful for solving shortest path problems in unweighted graphs, as it guarantees the optimal solution. By organizing the code into reusable methods and providing a clear example, we've created a template that can be applied to many similar graph-related problems. In this example, we are tasked with finding the shortest path in a graph with 6 nodes. The edges represent connections between the nodes, and our goal is to determine the shortest path from node 0 to node 5. To begin, we first construct the graph using an adjacency list representation. This allows us to store all the connections in a structured format where each node maps to its neighbors. For instance, node 0 is connected to nodes 1 and 2, node 1 connects back to node 0 and also to node 3, and so on. Once the graph is constructed, we initialize a breadth-first search, or BFS, starting at node 0 with a distance of 0. At this point, the queue contains only the starting node, and we mark node 0 as visited to avoid revisiting it during the search. The BFS begins by processing nodes level by level. In the first iteration, we dequeue node 0, which has a distance of 0, and explore its neighbors, nodes 1 and 2.
Both are added to the queue with an updated distance of 1, and we mark them as visited.
In the second iteration, we dequeue node 1, which has a distance of 1, and explore its neighbors.
Node 0 is already visited, so we add node 3 to the queue with a distance of 2 and mark it as visited. Next, we process node 2, also at a distance of 1, and explore its neighbors. Similar to before, node 0 is already visited, so we add node 4 to the queue with a distance of 2 and mark it as visited. The search continues with node 3, now at a distance of 2.
From here, we explore its neighbors, adding node 5 to the queue with a distance of 3 as it hasn't been visited yet. Finally, we process node 4 and its neighbors, though node 5 is already visited at this point. When node 5 is dequeued at a distance of 3, we recognize it as the target node and return the shortest distance, which is 3. The output for this example is 3, indicating that the shortest path from node 0 to node 5 consists of 3 steps.
Now, let's consider a different scenario. What happens if no valid path exists?
In this second example, we have only 4 nodes, and the edges are such that nodes 0 and 1 form one connected component, while nodes 2 and 3 form another.
Our goal is to determine the shortest path from node 0 to node 3. First, we construct the graph as before.
Here, node 0 connects to node 1, and node 2 connects to node 3. Nodes 0 and 1 are isolated from nodes 2 and 3, meaning they belong to separate components. We then initialize BFS starting at node 0 with a distance of 0, placing it in the queue and marking it as visited. The BFS begins by processing node 0, which has a distance of 0. We explore its neighbor, node 1, and add it to the queue with an updated distance of 1, marking it as visited. In the next iteration, we process node 1, now at a distance of 1, and explore its neighbor, node 0, which is already visited. At this point, the queue becomes empty, and we realize there is no way to reach node 3 from node 0, as they belong to separate disconnected components. Since no path exists, the algorithm returns -1 to indicate that the target node is unreachable. This demonstrates how BFS not only finds the shortest path but also confirms when no path is possible. Lastly, consider the case where the graph consists of only a single node, and the start and end nodes are the same. Here, we have one node labeled 0 with no edges. The goal is to determine the shortest path from node 0 to itself. First, we construct the graph, which simply shows node 0 with no neighbors. We then initialize BFS starting at node 0 with a distance of 0, placing it in the queue and marking it as visited. In the first and only iteration, we dequeue node 0 and immediately recognize it as the target node. Since no traversal is needed, the shortest distance is 0, and the algorithm returns this result. This example highlights the base case where the start and end nodes are identical, making the shortest path trivial. In this problem, we are analyzing the time complexity of an implementation that uses breadth-first search, or BFS, to find the shortest path in an undirected graph. The graph is represented as an adjacency list, and the analysis starts with the graph construction step. To build the adjacency list, we iterate over all the edges provided in the input. Since each edge is processed in constant time, adding 2 entries to the adjacency list for the 2 nodes it connects, the time complexity for this step is O(E), where E is the number of edges. Next, we look at the BFS traversal step. In BFS, each node is dequeued and processed exactly once, contributing O(N) time for n nodes. Additionally, every edge is traversed once throughout the entire search, which adds O(E) to the complexity. Combining these, the BFS traversal step has a time complexity of O(N plus E). Now, when we combine the time complexities of graph construction and BFS traversal, the overall time complexity of the implementation is O(E) plus O(N plus E), which simplifies to O(N plus E). This is the standard time complexity for BFS when using an adjacency list representation. Shifting focus to space complexity, we start with the graph representation. The adjacency list requires space proportional to the number of nodes and edges, as each node has a list of its neighbors. This gives a space complexity of O(N plus E). Additionally, we have a set to keep track of visited nodes. In the worst case, all n nodes could be visited, so the visited set contributes O(N) to the space complexity. The queue used in the BFS algorithm also contributes to the space complexity.
In the worst-case scenario, such as in a complete graph or one with high branching at each level, all n nodes could be in queued at the same time. This adds O(n) to the space usage. Combining the adjacency list, the visited set, and the queue, the total space complexity becomes O(n plus e). Next, we examine different scenarios for time complexity. In the best case, the start node is the same as the target node. Here, BFS terminates immediately after the first step, and no edges are traversed, resulting in a time complexity of O(1). In the average case, for a typical sparse graph where the number of edges e is proportional to the number of nodes n, BFS explores only a subset of nodes and edges before reaching the target. This makes the time complexity roughly O(n). In the worst case, the graph is fully connected, meaning BFS must traverse all nodes and edges to reach the target. Here, the time complexity is O(n plus e). To put this into perspective, we compare the BFS approach to a brute force method. A naive approach might involve generating all possible paths between the start and end nodes, then selecting the shortest one. However, this would result in an exponential time complexity of k to the power of n, where k is the average branching factor. Clearly, this is infeasible for large graphs. In contrast, the BFS approach is highly optimized, finding the shortest path in linear time relative to the size of the graph, O(n plus e). This is particularly efficient for unweighted graphs. The reason BFS is optimal is that it explores all nodes at a given distance before moving to the next level. This guarantees that when the target node is reached, it is via the shortest path, making BFS the best choice for this type of problem. When tackling algorithmic problems, there are several common mistakes that can trip you up. First, not accounting for edge cases is a frequent issue. For example, if your solution doesn't handle empty inputs, single-element arrays, or maximum constraints, you may encounter runtime errors. It's always important to test the extremes of input size and values to make sure your solution is robust. Another mistake is selecting an inefficient algorithm. If a problem requires optimization, relying on a brute force approach can lead to time limits being exceeded. Carefully analyze the constraints of the problem to choose the most appropriate solution, such as dynamic programming or greedy algorithms. Misunderstanding the problem requirements is another pitfall. Subtle constraints, like sorted input or uniqueness requirements, might be easy to miss, so it's crucial to reread the problem closely to fully grasp what's being asked. Additionally, while developers often focus on time complexity, ignoring space complexity can be just as problematic. Overusing auxiliary data structures can cause memory limits to be exceeded. Finally, incorrect handling of indices is a very common source of errors. Off-by-one mistakes or failing to check boundary conditions can derail your solution, so always double-check your index management to ensure it's correct. To excel in interviews, there are a few key strategies that can make a big difference. One of the most important is pattern-based thinking. Many problems fall into recognizable categories, like sliding window, two-pointers, binary search, or dynamic programming. The earlier you recognize the pattern, the faster you can approach the solution. It's also important to explain your thought process as you work. Not only does this help the interviewer understand your reasoning, but it also gives them an opportunity to guide you if you're going off track. Trade-off analysis is another valuable skill to demonstrate. Be ready to discuss the strengths and weaknesses of your solution. Does it optimize for time at the cost of space, or vice versa? This ability to weigh options shows critical thinking. Lastly, iterative refinement is a great strategy when you're stuck. Start with a brute force solution and then work to optimize it step by step. Even if you don't arrive at the most efficient solution immediately, this approach showcases your problem-solving process. Practicing related problems can help reinforce the concepts and techniques needed to solve similar challenges. For instance, LeetCode 121, Best Time to Buy and Sell Stock, focuses on finding an optimal solution with minimal space complexity. It's a great example of balancing performance with simplicity. Another classic problem is LeetCode 53, Maximum Subarray. This dynamic programming challenge emphasizes recognizing optimization patterns and applying them effectively. LeetCode 152, Maximum Product Subarray, builds on similar ideas but introduces the additional complexity of handling sign changes, which can be a tricky edge case. Finally, LeetCode 42, trapping rainwater, is a well-known two-pointer or dynamic programming problem. It's particularly useful for understanding the trade-offs between time and space complexity. Working through these problems will deepen your understanding of common patterns and edge cases. When solving problems, it's helpful to be familiar with alternative approaches and when to use them. A brute force approach is often the simplest to implement, and while it's usually inefficient for large inputs, it can be a great starting point to validate your logic on small test cases. Optimized iterative solutions, such as sliding window, two-pointers, or greedy algorithms, are tools that can significantly reduce runtime and are especially effective for problems with straightforward constraints. For more complex challenges, dynamic programming is a powerful method. It's particularly useful for problems with overlapping subproblems, and it often achieves a good balance between time and space efficiency. Finally, binary search is a key strategy for problems involving sorted input or optimization over a search space. By reducing the complexity to O log n, in many cases, it's an essential technique to master for efficient problem solving. Great job making it to the end. In this session, we explored how to approach a coding problem methodically, even when details are limited. Remember, breaking down challenges into smaller steps and focusing on the fundamentals is key. Thanks for watching. Be sure to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!